Hi there, this is Dave Newman, CEO of Brain Scanology, and this video is a follow-up from our previous one on glaucoma, in which we measured the shape of the optic cup. In this presentation, we measured the shape of both the disc and the cup together to quantitatively stratify glaucoma versus healthy eyes. So previously, we analyzed images from the Acrema dataset, as discussed in this publication by Diaz-Pinto et al. And just as a reminder, previously we outlined the shape of the optic cup and extracted that to measure its shape via Shape Genie. And I will leave out the methodological details. You can watch that in the previous video. But just as a reminder, this is the data that we found. We were able to find at least one index that stratified normal versus glaucoma well, and it's been 3. Here it is shown for Acrema dataset and the Drishti dataset separately and then combined. And since then, we have found more indices from this data that also give us a strong separation, and thus will be great for machine learning models that classify glaucoma. But at the end of that presentation, we proposed that it'd be a good idea to measure the shape of both the cup and the disc together in Shape Genie at the same time. Because many papers have found that the distance between the cup and the disc has been useful in stratifying normal versus glaucoma quantitatively. And so in this presentation, we did just that. Let me describe some crucial methodological details of how we did this. So first, we outlined both the cup and the disc, and we extracted the mask of both together. And then we found the longest length of the longest internal length of the cup, and we rotated that such that we rotated the image such that that line is horizontal. And we did this we align our data in this way in order to get cleaner data. And we do this because we find that nature is inherently polar, as in North Pole versus South Pole, anterior versus posterior, so on and so forth. And then when we align the data this way, we get much cleaner results. And I want to point out here that we had 2 options of aligning it, whether by the longest length of the cup or of the disc. And we found that when we align it by the longest length of the cup, we found much greater differences between normal versus glaucoma, as opposed to aligning the shape according to the longest length of the disc. So cup is more informative than disc. And another crucial detail is that we measured what we called pure shape. A lot of these images were taken at different magnifications, and thus the optic cups and discs were of different sizes between patients. And what we did was we found the longest internal length of the outer ring, that is the longest internal length of the optic disc, and we resized all of them such that the disc and anything within it had the same width, in this case 400 pixels. That's an arbitrary number, but we always constrain aspect ratio so that we do not skew the shape when we resize. But in this way, we're able to normalize the size of every single cup and disc, no matter what the original magnification of the fundus images was. And in this way, we measure pure shape, which is very special to what Shape Genie can do. Now on to the results. When we did this, we found a great index. We found several. I'm just showing you here one of them, in which we sum all the bins of the frequency plot that results when you measure this shape in Shape Genie. And we find that this index separates normal versus glaucoma very well in 2 different data sets. And so we're happy that we found yet another index to add to our list of indices. So far, we found about 5 that are great for developing a machine learning model. And given how well the scatter separates from each other, we're confident that we'll be able to develop a machine learning model that classifies glaucoma with at least 90% accuracy. And we will move forward in doing that. So I want to highlight that we find 5 numerical features stratifying normal versus glaucoma, and we did so simply by analyzing the shape of the optic cup and the shape of the optic cup and disc together. Right? We've yet to look at other features in the retina in these fundus images, but thus far, with these obvious ones, we've already found evidence that, in our experience, will yield a 9% accurate classifier. For those who are familiar with how the Shape Genie or the LCPC transform measures shapes in Shape Genie, you can stop watching here, but for those who are not familiar with it, let me take a minute to explain how it works. So if this is the shape of interest, right, you can apply the radial grid system in Shape Genie. That is, Shape Genie will find the center of the bounding box that encapsulates your shape, and the center of that rectangular box will be the origin of a 360 radial grid, and the software will then look for every intersection between the radial line and the edge of your object, as seen in step 3. It will then measure the distance between every single intersection to the red dot, and then it will turn this figure into a 2-dimensional series of x and y coordinates. And thus, this is called the linearization step, as in you've taken this circular or rounded closed object and linearized it. And then next, the software then applies a fast Fourier transform to this data and produces a frequency plot as such that represents the shape that you began with. And then here we have the option of creating a scalar value as an index. And what we did here was for this presentation, we summed all bins, the magnitudes of all bins into one number. And this is what we showed you here. See, the index called sum all bins. That's how we got scalar values representing each sample. And I just want to quickly highlight that in the case of the optic cup and disc together, right, each line will intersect the object twice, right, because there's 2 lines here. And anytime a radial line intersects an object more than once, what it does is it sums all the distances of those objects into one number, right? Thus, in the plot in step 4, the angle position is on the x-axis, and the y-axis, there's only one value per angle position, right? Even if that position had multiple intersections, we sum them all into one value, right? Thus, the word compressed in the name linearized compressed polar coordinates transform. Thank you for your attention.